Next, we will have Roshan from Marlin. He's going to talk about their ZK proof market design.
Hi, so I'm Roshan. I'm a researcher with Marlin, and basically building Kalypso, that's like a circuit-agnostic confidential ZK proof market. And it essentially lets you outsource proof computation to our network instead of trying to do it either yourself by running servers or more likely, by running it on your users' devices, right? So the reason we started building this was basically this, which is that ZK proof generation today takes way too long, and the primary culprit is like the underlying math behind ZK. Right? It involves a lot of like MSMs and entities that are really slow on consumer CPUs, and it's really compute intensive and for like relatively small circuits. So you can expect something around like 3 to 4 orders of magnitude of slow up compared to just running the compute directly, right? And given that compute time directly translates into the electricity and like the cost of compute, that basically means that proof generation today is like also really expensive, right? So just to give some rough numbers, these are from an app called like ZK Bob, which is I guess similar to Aztec ZK Money and stuff that uses like nodes and nullifiers to create payment transactions. And in my laptop, that's like kind of beefy. It takes up to a minute, single-threaded, and if you make use of like multi-threading, it does like 16 threads. It comes down to something around like 15 seconds, right? And on the left is a little old. It's from like RIS0, just doing like a SHA-384 on that, right? Your computer probably does like thousands of these as you're just browsing around the web, right? And this doesn't even include other parts of like certificate verification, like for example, certificate change and all that stuff. So, I mean, these numbers aren't really that bad. I mean, they aren't great, but they're still workable, right? Problem is that it's way worse in browsers, which is where I use most of my dApps today, right? Because you're sort of like limited to the JS or like WASM sandbox that you have over there. And what that means is you don't really get to use the full set of like CPU instructions like that you can probably use in like native code. So the 15-second thing in my laptop suddenly jumped up to something around like 30 to 60 seconds in my browser, right? But it's actually even worse on like mobile devices, which is like the most important application platform in my opinion today. And that's because, I mean, my phone is pretty beefy, but it still has limited hardware compared to my laptop, right? And you suddenly have an extra dimension of the battery capacity. You don't really want to keep generating proofs on a user's devices because that then affects the battery usage of the device and the battery life and all that. So something that took around a minute on my laptop suddenly starts taking like up to 4 minutes when I try to do it on my mobile phone, right? So, well, I know what you guys are probably thinking, just optimize, stop complaining, right? Problem is that, well, for one, it takes immense resources. We have quite a few teams over here who are like experts in all of this. And turns out that it's a really different skill set from like the usual software engineering that you do, right? And what that means is that not every project has, or like in my opinion, should have like a ZK team who's focused on like optimizations and all that. And okay, even if let's say I have like a good ZK team, it's still really hard to optimize it on common hardware, which is why we have all the like FPGA and ASIC projects popping up. And fine, let's say you still do that, you still can't rely on your users having any sort of like specialized hardware, right? They're still just gonna have their laptop normal CPUs and maybe a GPU if you're lucky. So let's look at like how optimization actually works in the real world, right? So you essentially have a positive feedback loop. So hopefully you have some demand from your users for like faster proofs. Your ecosystem basically now gets to serve a bigger target market for the proofs and with like higher expected profits because you have a bigger market. And what that means is now people can like justify investing into more like risky improvements, like for example, maybe an ASIC or like an FPGA for your proof system. And hopefully that makes your proof system faster, and that hopefully gets more users into your application, and round we go, right? So this is why we basically started building Kalypso. So the main goal is to make proof generation faster and cheaper. It's to get the optimization flywheel spinning for your project, right? it's a much more efficient use of your resources because like teams are running servers to generate ZK proofs on their own. We can get way better utilization by like amortizing all of that cost across different projects and like proof systems and all that. And like it puts you on the path to a decentralization, so you don't have to do things yourself. So yeah, this is basically what Kalypso is. It's sort of structured as a marketplace today. So you have on one side, you have all the applications that require ZK proofs to be generated, for example, roll-ups and like all the end user applications. And on the other side, we basically have a hardware network that has like much better utilization of resources. It's stake secured, so you get guarantees on like response and uptime and all that. And it's like way faster because they can afford specialized hardware that's like amortized over the entire proving set. And the last thing I want to mention is something that's fairly unique is the network currently supports private inputs. So you can sort of like outsource proof generation that you might be doing on a user's devices without compromising on like the privacy aspect of it. So the marketplace is circuit agnostic because the core protocol itself operates on like circuit agnostic abstractions. They're just like a bunch of smart contracts and like interfaces that you can just plug and play all of your popular ZK circuits and VMs and all that stuff into. And like it's really easy to add. I just tried it with like Jolt yesterday, managed to do it in like an hour or two. And something that we're looking forward to is some sort of like common developer tooling that lets you, sort of evaluate all the popular ZK circuits and VMs there are for your application. Sort of make like a comparison, benchmark, pick the one that's like more suited for your application. The way we support private markets is through enclaves. So these are like hardware level isolated and like encrypted environments that like isolates the code of the prover running even from the host, right? So it while this is like secured by enclaves, it doesn't affect the security of your application because at the end of the day, it's still fundamentally ZK. You get a ZK proof out of it, and it either verifies or doesn't matter if it was generated inside an enclave or not. And it's like built into most new CPUs that you get today. And like we're quickly adding support for like GPUs from NVIDIA as well in terms of like secure enclaves. So the market is secured by crypto economics. So you have provers that like stake tokens that are allocated against each job. You have provers providing like liveness guarantees for your job that the protocol basically enforces through slashing, right? And the cool part is we managed to do it in a fully automated fashion without spreading up either the stake pool or the compute pool between like different markets or like different applications, right? So looking ahead a bit in terms of like what we have or like what is in the works currently, unified Stark markets is one big thing because like Stark circuits basically have a wide range of I guess like compute time and like compute price in terms of what you can compute with them. So some sort of like unified Stark market would be great. We're quickly working to onboard like confidential computing powered by GPUs as well. So you can have your private market proofs generated inside a GPU. Proof aggregation is something we're looking into. You can kind of do this today by just creating a new market for proof aggregation, but some sort of like mechanism design or like crypto economics around that would make sense. And also looking at like alternative front ends. And I don't mean that in UI sense, I mean that more in like a compiler design sense. So currently the way Kalypso is structured is more of like a marketplace, like you have an order book, buy orders, sell orders that basically feed into the backend that handles all the settlement and all that. Kind of looking at alternative front ends, for example, maybe auctions or like proof races and stuff like that, that can sort of like feed into the same compute liquidity pool that you have, right? So last time I was here, Kalypso was still in private beta, but I'm happy to announce that it's currently live. You can just go and look at the docs and start using it today. And so you can participate as a prover, just set up some hardware and the prover software. You get to pick which markets you want to support. You get to choose your own pricing and timings that you register on Kalypso, right? And you can also participate as a dApp. Just create a market for your dApp. Just wait for some generators to join, hopefully. And I guess if you have some sort of like novel proof system where you're probably the first person who's creating a market with that, you might have to create some, I guess, like reference provers, verifiers, and benchmarkers to like sort of just bootstrap the ecosystem, right? So if you're building something cool, hit me up after the talk. We'll be happy to like provide access and credits and all of that stuff as well. So yeah, I just want to sign off with just this. Think about like leaving your proof generation to a proof market and just like focus on what you do best, right? Which is just building your application. So thank you.
Thank you, Roshan. Oh, we got a question there.
Thank you. Could you talk more about how you support private inputs?
Yeah, sure. So essentially, it works through enclaves. We basically have like hardware-isolated environments that run the provers that are actually generating the proofs, right? So your users basically get to set up like secure channels with the hardware that even the guy who's like running the hardware can't really observe, if that makes sense.
Yeah. What enclaves do you run on?
So currently we are supporting like Nitro and like SEV SNP, right? Try to stay away from SGX for obvious reasons, I guess.
Performance reasons?
Sorry?
Performance reasons?
No. I think SGX is it's a little prone to like side channels because of the way the enclave just works, right? You sort of have, I guess enclaves sort of like come in two flavors. So one flavor is where you have untrusted code that's running alongside trusted code, right? What that means is that when you basically have untrusted and trusted components running on the same core, you sort of have like internals of the core leaking out, which is how you get all the side channels with like cache attacks and this and that, right? The other flavor which we prefer is where your enclaves essentially have like dedicated hardware assigned to them. So for example, some cores on your CPU are like dedicated to a specific enclave, or like some memory regions are dedicated to a specific enclave. And these sorts of enclaves are like way more resistant to like the side channel attacks and stuff that you see.
Thank you. May I ask a question?
Yeah.
I'm curious how you consider the MEV capture and distribution in your product.
Right. So at least the way we tend to think about it is we sort of don't really want to be in the pipeline as such directly, right? So for example, we are in talks with a lot of like blog builders who are like interested in using this and stuff like that. So it's kind of actually it comes down to the problem of like having an alternate front end, right? So the way it currently works is like it's structured as a marketplace, which means you have like buy orders and sell orders. And that doesn't really translate directly into something like proof of stake based prover pool or something like that, right? So the way it currently works is we sort of just act as the backend to people who are actually registered in like different rollups and chains, and they just sort of use the proof marketplace as a backend currently.
Thank you. Oh, one more question.
I actually want to ask a follow-up question on privacy. So how would you define the trust model between the client and the prover? Like what does the prover, what is it limited to?
Got it. So I guess at the end of the day, it does comes down to the trust model of the enclave that you have, right? So that's obviously non-negotiable. You trust that the hardware enclave that's implemented is like a good implementation. There's no real bugs there and all that stuff. But apart from that, you don't really need to trust anybody. So in terms of setting up the secure channel, the key is basically generated inside the enclave itself. And we essentially use like a derivative of like TLS to sort of like set up an end-to-end secured pipeline between the user and the enclave.
Maybe I'll make it more specific. Do we expect the prover to know everything? Like, do I pass the private information to the prover?
Yeah, we do. Currently, we do. What you're working on is also sort of like trying to not do that using some form of like MPC between different, I guess, like enclave flavors. For example, you might have one AMD enclave, one like Nitro enclave, or one like other flavor. And you sort of like have MPC between the three. So even if one gets compromised, it doesn't really matter in the big picture, right?
Thank you. Thank you, Roshan.
Thank you.